wrapping up another nice short unit. Unit 7 only has 3 sections as well. So linear versus exponential. So we've been talking about exponential growth and decay in this unit, and now we're going to compare it with linear. So we need to be able to look at word problems, graphs, T-charts, and know, are we talking about something that's linear or exponential? So let's just do some basic graphs. So we have f of x, and we know that this is linear because it's y equals mx plus b, and we know that this is exponential. So we should already be able to recognize based on the equation which one it is. Of course, linear y equals mx plus b, and exponential, you have a variable in the exponent. Okay, so if I'm graphing these, I remember how to graph a linear equation by starting with the y-intercept. So here's my y-axis. I plot a point at 1. And then from there, I'm going to count my slope. My slope is 2 over 1. So I go up 2, right 1, and I can keep doing that. Up 2, right 1, up 2, right 1. And then I can draw a nice straight line in there. And then for my exponential, maybe you want to do a T-chart for that. That's kind of how we've been doing it. Makes it pretty easy. So if I start with 0, 2 to the 0 power, well, anything to the 0 power is 1. 1, 2 to the first power would be 2. 2, 2 to the second would be 4. I could keep going. I could do 3, 2 to the third power would give me 8. I could have even done negatives. If I did a -1, maybe you need your calculator for that. That's fine. You would have gotten 1/2. So plotting what I have here, 0, 1. So they have the same y-intercept. 1, 2, 2, 4, and then 3, 8. Definitely helpful to get a couple in there, because if you just did these first 3, you might be like, oh, that's linear. Even though it's not, you might get tricked. So make sure you do enough that you can really see that exponential curve. You know I'm terrible at drawing these on here. But it should look something like that. So again, we should already know whether it's linear or exponential based on the equation, and that is all about, to be exponential, you have to have a variable in the exponent. Okay, so now we have word problems. So we have to identify the type of relationship and create a function from the given information. Well, what types of relationships are we talking about? Well, if it's linear, you could have growth, so you would have a positive slope. You could have linear decay. So growth and decay aren't terms just for exponential. That's just meaning increasing and decreasing, positive slope and negative slope. And then along with that, you could have exponential growth, which was section 7.1, or exponential decay, which is section 7.2. Okay, so maybe jot these 4 types of relationships off to the side there. So those are your 4 options. Oh, that didn't really change the color. There we go. Okay, so I have a savings account, S, and by the way, when you're doing these, you want to use the variables that they're giving you. So if they're giving you a specific variable, you should not revert to X and Y. Use what they have. A savings account S has $500 and accumulates no interest, but receives a deposit of $825 per month, M. So I have my S and my M. What is this, linear or exponential? Hopefully we're seeing that it's growth because you're receiving a deposit, so we know it's got to be growth. Is it growing linearly or exponentially? There's different ways you could figure this out, okay? But regardless of how you're doing it, whether you decide to make a T-chart, whether you decide to just think it through, hopefully you're going to recognize if you're adding or subtracting a set amount each time, whether it's per month, per day, per year, per hour, whatever, a set amount of money or a set number of items, that's going to be linear. Exponential is going to turn or happen when we have percents. So linear growth and decay are more of a set specific number. Exponential growth and decay are when you're talking about a percent. So in this case, we are talking about linear growth. So we should be thinking y equals mx plus b, but we need to use their variables. What are we trying to figure out? We're trying to figure out a total amount of money. So the savings account S has $500 and accumulates no interest, but receives a deposit of $825 per month. Well, in this case, I think it's actually easier to go backwards and think kind of B plus MX because I'm starting with a set amount. That set amount is $500. It's receiving, so plus $825 per month, so 825 M. Because if I were to have it for 2 months, I'd have to do 825 times 2 plus the 500. Okay, so there is my function. If you want to be even better, you should use function notation. Function notation still uses the same variables, but it says S of M equals 500 plus 825 M. So it just says we're taking it of our dependent variable, which is M. Okay, the value V of a house is 150,000 and increases by 1.5% per year. So that goes back to what I said down here. If you see that you're increasing or decreasing by a percent, you should be thinking exponential. Exponential is always y equals a times b to the x, and then you have to do some extra stuff in there. In this case, we're trying to find the value, so y is our value, equals A is your initial amount, so in that case, this is $150,000, times B, well, in this case, because we're talking exponential growth and we've been given a percent and not a growth factor, so it doesn't say it's multiplying by 5 every month or something. That would just be the growth factor. That would just be your B. But in this case, it's a percent, so remember that percent, or that B is 1 plus your percent, and that percent has to be moved into a decimal. So times 1 plus, well, 1.5% as a decimal, you've got to move your decimal 2 spots to the left to turn something from a percent into a decimal. So 0.015, and we're not to the x anymore, we're to the t, which stands for years. If you want to write this as 1.015, you may do that. Clean it up one more time. I wouldn't take off if you didn't do that, but you certainly can. Okay, we need to be able to do the same exact thing from a t-chart. So first we would like to make sure we're, working in the same increments here. So we're going by ones, that's great. And then what are you doing from here to here, here to here, here to here? Well, you might first think I'm subtracting 3, but then immediately you realize, okay, but I didn't subtract 3 there. So linear should be out of your mind. It's not subtract 3 every time, so it's not going to be linear. Then you should be thinking, is it exponential? Well, I've got to figure out what I'm multiplying by to get from 15 to 12. 15 times some number has to give me 12. Well, think about how to do that. The shortcut is just divide. Take 12 divided by 15. Okay, because if you were solving this equation, that's what you'd have to do. And also, that's the shortcut I showed you before. 12 divided by 15 is 0.8, so I must have multiplied by 0.8. Let's try. Is 12 times 0.8 going to give me 9.6? Check it out in your calculator. Sure, it does. And then 9.6 times 0.8, does that give me 7.68? And it does. So I'm talking exponential. Is this growth or decay? It is decay, and I should have written that back here. I didn't. So this one I should have first said exponential growth. Okay, so make sure you do write that because I will look for that answer and the equation, since that's what your directions are telling you to do. So over here we have exponential growth. I'm sorry, decay on this one because we are going down, we're decreasing. Y equals your A is your initial amount. Remember, it's not necessarily your first number. It has to be matched up when X, your independent variable, is 0. So in this case, it is the first thing, and it's 15 times B. Now, we're not talking percents here. We simply have a decay factor, so you don't have to mess with any of that 1 plus or minus stuff. It's just your growth factor, which goes in right here. Actually, it's a decay factor, 0.8 to the X. Okay. Next one. Your T's look good. You're going up by 1 each time. Down here, my first thought is I added 5, and that's true here and here as well. So that makes this linear, since you are adding the same number every time. and it's going to be linear growth because you're increasing. So exponential, you need to be multiplying. Linear, you need to be adding. Even if it's adding a negative number, and exponential, even if it's multiplying by a fraction. So y equals mx plus b. Y equals your starting point, again, has to be when x is 0, or in this case, t is 0. So your y-intercept is 10. And then what are you doing every time? You're adding 5. So that's your slope. So y equals 5x plus 10. Okay, we also need to be able to do the same thing from a graph. Graphs are really easy to see if they're linear or exponential right away. So obviously if it's a straight line, it's going to be linear. This is going down, so it's decay. And if it's this curve, the exponential curve, then clearly it's going to be exponential. This one is also going down, so that would be decay as well. Okay, so we know it's linear, so we're working y equals mx plus b. So you need to know two things. You need to know your slope and your y-intercept. Well, your y-intercept is when your line crosses your y-axis, and there it is. The x value is always going to be 0, so we just need that y value, which is 6. And then count your slope. So you're going down 1, 2, 3, 4, over 1, 2, 3, 4. So down 4, over 4. Don't forget you need that x in there. And then simplify that. What's negative 4 over 4? It's just negative 1. So you could have even just counted down 1, right 1. That's your answer. Exponential decay. So we're talking y equals a times b to the x, exponential. Y equals, a is your initial amount. Your initial amount occurs when your x is 0. So that's right here. It's your 8. You can actually think of your b in linear as your a in exponential. They're both the y-intercept. A little confusing because it's a b here and there's b here, but it's not the b, it's the a, but hopefully you're okay with that. Then you need to figure out your growth or decay factor for your b. So we're not talking percents, we're simply talking what did you multiply by to get this? Well, what did I multiply 8 by to get 4? You might think you subtracted 4, but remember that's not exponential, that would be linear. And this is clearly not a linear graph. Your next thought might be, okay, I divided by 2. But we can't talk in terms of division, we have to talk in terms of multiplication. So what is division by 2 the same as in multiplication? It's the reciprocal. The reciprocal of 2 is 1/2. So you have to multiply 8 by 1/2 to get the 4. And then you need, of course, your exponent up there. Okay? If you're not sure if you have them right, you can always plug in a point. So here, if I plug 4 in for my x, so I would have y equals negative 1 times 4 plus 6. I get y equals negative 4 plus 6. I get y equals 2, and that's what I wanted to get. So that's just a quick check to make sure you have the right equation. Over here, if I plug in 1 for my x, I should get 4. Let's see. I have y equals 8 times 1/2 to the first power is 1/2. 8 times 1/2 is 4, and that's what I wanted to get. So you can always check these. You could even find a point that's on here that's not labeled. Try one of those. It should work if you have the right equation. All right, doubling time. An initial amount a that doubles every x. Okay, so the formula for that, if we're trying to double something in a certain amount of time, is f of t equals a times 2 to the t over x. Well, a is your initial amount, x is how often it takes to double, and t is going to be some amount of time that your problem talks about. Okay, so let's do an example and it'll make more sense, I think. But notice this is exponential because your variable is in the exponent. Create a function that models each scenario, then answer the number of people p living in a city doubles every 30 years t. If there are currently 7,000 people in the city, how many will live there in 50 years? So f of t is what we're looking for. We're looking for how many people will live there in 50 years. So this isn't actually t. Now let me do it in 2 steps. I'm getting ahead of myself there. Let's plug in the base stuff before we answer the question. So A is your initial amount. What's the initial amount here? 7,000 people. Times 2. Why is it 2? Well, of course, because we're doubling. And then to the t over x. Okay. And then you need to figure out where the 30 goes as opposed to where the 50 goes. Which one of them is the basis of the information? Well, the 30 is. The 50 is asking a specific question, but it's saying it doubles every 30 years. However many times it doubles, that's your x. It doubles every x. So even though they're calling it t in this case, it's not the t here, it's the x. The number that it doubles, that goes on the bottom of your fraction. Okay, the top number is your t variable. So in this particular case, they are asking us specifically to find out what happens in 50 years. So t is 50. Again, I know it's confusing because they're using a t here for 30, but that's not what they're talking about in that case. So it's 50 over 30. The bottom number is how often it doubles. The bottom number is how long it takes to double. The top number is what year we're trying to find out, and that happens to be 50. Keep in mind that is an exponent, not multiplication. So you would be typing in your calculator 7,000 times 2 to the, and you need to put the 50 over 30, all of that in your exponent. We get that f of 50 equals 22,224 people. We got to round that. Okay, so that's how many we are predicting will live there in 50 years. Okay. And you can kind of think that through. If in 30 years it's going to double, that means in 30 years there'd be 14,000 people. Well, in another 30 years, which would be 60 years, 14,000 would double and get you to 28. So it makes sense that we should be between 14,000 and 28,000. Okay, there are 3 cockroaches C behind Mr. Brust's microwave. Yuck. And their population doubles every 14 days D. How many cockroaches will there be in 40 days? Okay, so f of t equals A is your initial amount. Your initial amount are 3 cockroaches. It's doubling, so of course we're using our doubling equation, which is a 2. How often does it double? So t over, it doubles every 14 days. However long it takes to double, that's the bottom number of your fraction. Then to answer the question, how many cockroaches will there be in 40 days? We need to find f of 40. So 3 times 2 to the 40 over 14. Because what you end up finding, if you just do 40 divided by 14, you get like 2.86 rounded. So what that's saying is that you're doubling it 2.86 times. Okay? And then if you, so if you're taking 3 and doubling it 2.86 times, you would get your answer that you'll calculate here. So f of 40 equals 3 times 2 to the, and don't use that 2.86, use the exact 40 over 14. I just was explaining what you were finding there. 21.7, so we can round that to 22 since we're talking about something that has to be in whole numbers. 22 cockroaches. Yuck. Better call the exterminator. Okay, along with doubling, we can kind of go the opposite way and talk about halving or half-life. And this is something I think you've talked about in science class, or at least hopefully you did at this point. And it's an initial amount A that's shrinking by half every x. So it's almost the exact same equation. It's just instead of a 2, it's a 1/2. So really any time that you are aware of something tripling in a certain time period or quadrupling in a certain time period, you can use this. You just have to change what that growth or decay factor is. Half-life is generally used with radioactive materials, and it's how long it takes for half of the substance to go away. Usually decomposing is what we're talking about in science applications here. So if you start with a certain amount of material, The half-life is how many years, days, weeks, whatever it takes for half of the material to go away, and then you would continue to half it. So hopefully you can picture that that would be an exponential situation, which is why you have an exponential equation. All right, so f of t equals A is your initial amount. Well, there's 500 grams. That's your initial amount. It's half-life, so there's our 1/2 to the t over, it's 5,700. The half-life is your x. That's what goes on the bottom. And then when you answer the question, you're finding what was happening 20,000 years from now. So 500 times 1/2 to the 20,000 over 5,700. So again, what you're finding, what this part is finding, is how many half-lives we're talking about. But you can put the whole thing in your calculator, 500 times 0.5 to the, make sure you get that whole fraction, the 20,000 over 5,700, all of that in your exponent. And our answer is, there would be 44, or let's round it to the nearest 10, 43.9 grams of that radioactive material left 20,000 years from now. Pause the video. You guys try this, the very last one. Okay, so first check your base equation here. P of m, using the variables they gave us and function notation. So the population after m months is 1,700 times 1/2 to the m over 6. Okay, because 6 months is how long the half-life, or how long it takes to shrink by half. And then what we need to find is not P of 5. Be careful. We're working in months here and years here. So 5 years is how many months? Well, 5 times 12 is 60. So if you found P of 5, you got tricked there. You've got to make them in the same unit. In this case, we need them in months. So 60. Okay, and then calculating that. Gives me 1.6, so roughly 2 rodents. Okay, so they've almost been eradicated after 5 years. Okay, keep on chugging, guys.